All right, we'll continue with the morning session. The next speaker is Wang Gaiten. He'll tell us about optimization of a Ti-Sapphire Mode-Locked Laser for higher harmonic generation and gallium nitride.
So he already said the title, so I'm not going to. I was mentored by Steve Clendiff, who's currently in China, and Chris, who's in the back. So I'm going to explain what all this means. First, this is the group. That's Steve, Shin, Blake, then there's the undergrad in the middle, I forgot his name. Chris, and then Adam, and then Grace. Grace is about to graduate. Yay! So I do what we call pulse lasers, which instead of having a continuous phase laser, which is just, one oscillating wave, there's a period of darkness, and then one big pulse, and then again, darkness. So what that gives us is that we're able to have a low average power, and then all the power is concentrated into these short pulses, which can go from pico and nanosecond used by Q-switch pulse lasers to femtosecond, which is used by mode-locked lasers, which is what we do. They provide all this stuff, which you can ask me about in the questions, because I need to unfortunately move on. And so we use a femtosecond scale laser. Here is a diagram of what most of the cavities look like. And what is mode locking? So what happens is we pump green, really high power green light into a titanium doped sapphire crystal. That's our red little rectangle right there. And then it fluoresces. And it fluoresces a really wide red and infrared band. And then all of these wavelengths then start resonating inside this cavity. And those are all the modes of the different wavelengths. And then what happens is once we perturb the intensity a little bit by perturbing the prism, something called the Kerr lens effect, which is some nonlinear optical effect, which you can also go into during questions, kind of lenses all of these and combines them so they cohere into these really short pulses. So we use this for their high peak power. They can also be used for spectroscopy, which we don't that much, our group does, MBCS. But we use them for, since they have really high peak power, for high harmonic generation, which is a nonlinear effect in any material. It started with atomic gases, which is really simple, but since they're gases, you hit not that many particles with the laser. So eventually there's been transitioning to solid state high harmonic generation, which can hit a lot more particles with the same laser. It becomes a lot more efficient, but it's not as studied, and there's two different mechanisms that govern what happens with high harmonic generation. It's called high harmonic generation because you have the fundamental laser wavelength, which is kind of like a standing wave. And then you then generate harmonics. So you generate this harmonic, which is twice the frequency photon, and then the third harmonic, and then etc. Except in solid state, because of inversion symmetry, you only get odd harmonics. And anyways, that's what happens. And then in solid state, it's governed by two different mechanisms, inter and intra-band electron motion, so both moving between bands and within its own band, which is really interesting. But again, please ask me during questions because I got a lot of stuff to talk about. So applications. The good thing about high harmonic generation is you can get a really high energy photon from a low energy fundamental. So we use, for example, 800 nanometer center wavelength. Some people use 2 micrometers, which is infrared. But then out of that, you can get UV lasers emitted, which are really useful for biology and biological purposes because they need UV lasers. Ask the biophysics people, I don't know why they need UV lasers. And also for frequency combs and attosecond dynamics. Since what happens is when you shoot a femtosecond pulse into something that emits high harmonics, if you get a high enough harmonic, the pulse compresses because it's a higher frequency, and then you get attosecond pulses out, which are 3 orders of magnitude faster, which means you can, everything good that comes out of femtosecond pulses are even better when you get 3 orders of magnitude faster. And since there's theory developing about how this happens in solids in inter versus intra-band dynamics, you can then reverse engineer and know how the band dynamics operate from, say, their harmonic generation, which is really important for solar cells and other semiconductor applications. Most of this is in semiconductors because of the whole band stuff. And so our summer goals were to first achieve a fast enough pulse with a lower rep rate. Rep rate is pretty much how many pulses are in some given time. If you have too many pulses, then your average power is divided along too many pulses, and it's not a high peak power. So if you have less pulses, then your average power is divided into less pulses, so the peak power is going to be higher. And if you have the same average power, then your sample will be damaged, because if you have too high of an average power, the sample will just get burned, which is what was happening before I got here. And so we tried to lower the rep rate, which basically just, we did it via something called telescope extension, which we take the original cavity, which I showed you guys, and then you just add this is the image, and then you just add a lens at 2 times the focal length, and then you get the image created. So this is the original beam, where it's supposed to come out, and then we just extended it, and now it's coming out of this guy. And so the pulses have to travel this much longer before they leave, which then lowers the rep rate. Oh, it's just really hard because it's more optics in the setup. We used a curved mirror, which can introduce some astigmatism, which I'll talk about if you have some questions, which is really pain in the neck. And so we did that, and it's also a lot harder to mold lock because it introduces, so this is one mirror, curved mirror, that introduces 6 new degrees of freedom inside the cavity that needs to be calibrated. So it's really hard. And then once you do that, we hit it into this vacuum chamber. This mirror gets concentrated to a lens onto the sample, which then emits high harmonics, which is why it's blue, into this spectrometer chamber, supposedly. And so another thing is to be able to do this in a vacuum, because currently the only harmonics that were generated in gallium nitride were above vacuum UV, because below a certain wavelength, air absorbs UV light, so you can't see unless you have a vacuum. So we have to do this in a vacuum, which involves having electronics to steer these things, because the harmonics come out at different angles while you're vacuuming, which is not easy and requires a lot of controls. So the challenges, like I said, astigmatism is a big thing when you're adding more lenses to your cavity. It's really hard to get a stable mode-locked pulse when you have when the beam is travels so much that any perturbation kind of breaks it, because it's really sensitive. So if the air moves, or if you cough on it, or if you talk from the room next to it, it can break. And so and this is made worse the more the beam travels inside the cavity. Like I said, high dimensional parameter space. I'll show you a diagram in a second, which means there's a lot of knobs to turn to calibrate it, which is really hard to achieve. And then so I learned how to laze and mode lock it, and then I also improved the spectrum analysis, because once you get Fourier theory, right, you have a lot of wavelengths happening in the cavity, so they combine to get a really short pulse. And the more wavelengths that you could cohere, the shorter your pulse is, because of the inverse relation. So we wanted the broadest spectrum possible to get the shortest pulse. And then so here's the cavity that ended up happening. This is a picture from 2 days ago. It goes into here. This is a titanium sapphire. This is a curved mirror. The titanium sapphire reflects off of this into this mirror. This is a telescope extension, and it comes out this way. And it comes. This is the apple coupler where the laser comes out of, but then also gets reflected back into this, which then comes through this side into this prism, this mirror, to this prism, and this mirror. The prisms kind of are what dictate most of what's going on, because you have to balance normal and anomalous dispersion, and then also higher order dispersion to get what pulse you want. And it's not really simple. You can get mode locks in the typical anomalous dispersion regime, which tightens your pulse, group velocity dispersion. But then also if you have something called Kelly sideband, which are soliton kind of peaking. Solitons are something else. You can ask me, they're balanced pulses. Then you actually want to go to the normal group velocity dispersion regime, which is harder to manage. This is some videos of trying to mode lock. Here's the oscilloscope response. As you can see, when you perturb it, you can start to get pulses from the oscilloscope. Then the camera, that's the image of the pulse. And then here's what the spectrum looks like when it's trying to mode lock. As you can see, it starts getting really broad when you're close to mode lock, and that's what you want because you want the broad spectrum. This is just CW. And then here's what some pulses look like. This is the spectrum and frequency. This is the time domain. We want to get hopefully sub 20 femtoseconds because the shorter your pulses, the higher your peak power. This is the spectrum analysis what I was talking about. I added titles and also noise processing. And then here's, there's an error in the x-axis. It says femtoseconds, but then it also says 10 to the minus 13. Ignore the femtoseconds, it's 10 to the minus 13. And then 1, which is 100 femtoseconds. This is some spectrum we got. So if you get double pulsing, which happens when you have a lot of power in your cavity, so it ends up having 2 pulses where there should be 1. They tend to interfere and have an interference pattern like this, like a normal interference pattern. And then here's a really bad mode lock. As you can see, the spectrum is incredibly tight, so the time domain is going to be incredibly wide. That was 267 femtoseconds, which is actually faster than what most labs use here, but way not enough. And then here's what we got recently, which is 27 femtoseconds, which is faster than what some of our labs use for MDCS. I think they use like 60 femtoseconds, but still not good enough for us. We use up 20. And so what did I do? We actually got, this is a picture from yesterday. I finally got the fundamental beam into the vacuum chamber. That little very light dot is the beam. I saw that there's like kind of phase transitions in when you mode lock, where it'll look like a good Gaussian and then it'll kind of split to what we call the Batman shape. And there'll be a lot of different things depending on how much dispersion you introduce to the system. And we want the Batman shape, and sometimes getting that depends on how you balance dispersion. More efficient mode locking process, but we've been doing this for 2.5 months, so we're getting kind of better at it. It's still really hard. Centering and aligning the experimental setup. We actually haven't done this. Me and Chris have not done this before, so it was our first time actually shooting things in the chamber and aligning them, which was kind of the past week. Perspective sharing, we have more people talking. Then this version compensation, we talked about getting rid of these soliton Kelly sidebands, which is something that had not happened before, and we're trying to correct with the prisms, but it's still work in progress. And then today, I'm trying to aim this morning, I tried to aim the fundamental into the chamber so we can start actually seeing getting harmonics, because the pulses are actually starting to get short enough for a little bit and then they break and then you lose it, because it's the parameters are like 18 or something. So if you tweak something, and it's not like a nice n-sphere region where if you're in it, then you just navigate the region, find mode lock. It is not nice. So you can imagine 17-dimensional space. Really easy, right? There can be mode lock region like here, but then there can also be one like here. And then they will be completely different, behave completely differently. And you can completely get lost in between them. And so we're looking for the fundamental, which is 800 nanometers. And so we background corrected, but for some reason when we take the signal, we get the correct peak in negative intensity. And then I'm like, is this real? But I kept pressing take signal to make sure it was repeatable, and the same thing happened every time. And then I'd cover it, and then you get the same peak in the same place, but positive when the light is not going into the chamber. So no idea what's happening, but it is background corrected, so it's signal that's coming in, but it's completely wrong. And that's as far as we are right now. And thank you, here's our group picture. Thank you for Myron and Jim. You guys are awesome. Steve, who's not here, Chris, who's the best, and everybody who's participated. And if you have any questions, contact me or ask them right now in the question section.